Okay, we are going to start our Tuesday session with the first talk by Valentina Puletti from University of Iceland, Probing Dynamics, oh, you see the title, of stringy flux tubes in large arc charge.
Thank you very much. Sorry, it's a long title, you're right. Well, first of all, let me thank the organizers for giving me the opportunity to talk here. And this is going to be a talk based on a work in progress with Davide Bonomi, Valentina Florini, Luca Griguolo, and Domenico Seminara. In particular, Davide and Luca are here among the audience. I have some problem in switching of the slides. Let me go like that. I think so, because the pointer works. But maybe I can do it by hand.
No, but can you try again?
Like that?
Ah, that's better. Can you try again?
Now, thank you. Okay, good. Our motivations. Well, I guess I don't have to explain this audience the importance of Wilson loops. Of course, these are very important, observable, gauge invariant, no local. And they have showing very interesting properties, for example, in playing an important role in confinement, the confinement. And I guess also I don't have to explain, but I want to say, because at least it's my personal motivation, how important to study certain objects, indeed there's a Wilson loop within n equal 4 super young males in 4 dimensions, but also other, let's say, key in QFT. And my personal motivation is because this gives you an interplay which is quite ideal and amazing to study, to show how different notions and techniques coming both from quantum field theory and from string theory play an important role and then can combine together. So that's as I say, my personal interest in Wilson loop and the formation, and in particular in the SCFT. And as I say, my personal interest is that it could help also to understand a bit better what's going on the string theory side. And okay, in this talk I will focus on a particular family of observables and in n equal 4 super young males. And this is what's called cusp Wilson loop with local insertions. So they are deformed by a geometrical angle that I'm going to call cusp. They are deformed by orientation angle, sometimes I call it also internal angle, theta, and by the insertion of local operators. And this is general, so I'm going to be precise in a moment. But the goal is that I want to study this Wilson loop from the point of view of the string theory. And in particular, the goal is to go beyond the classical level. And the question that I'm going to try, at least partially, this is a work in progress, is going to try to understand which are the features that string theory, or at least the dual string theory, can capture about these observables. Okay, and please, if I'm saying something not clear, just interrupt me and ask questions. So I'm going to try to review a bit, very quickly, what these objects are in n equal 4 super young males, and then I'm going to review the classical solution dual to these observables, and I'm going to try to go through an example a bit more detail, on a specific example which is called the anti-parallel limits, and see what's coming out of this analysis. And then, okay, let's see how far I go, but I'll try to also go to the one loop level and discuss outlook and extension. Okay, part 1, field theory. So let me start to be precise. Of course, the central object here, it's the Wilson loop. Well, let's say the Wilson-Maldacena loop in in n equal 4 super young males from the field theory side. And just to be clear, I'm going to work only in the planar limit, so n is very large here for us. And at some point, I will switch also to the strong coupling. This is, of course, the general definition, but I'm going to be interested in a very specific case. And what do I mean? What we call the generalized cusp. So I'm going to place first the theory on R times R3, and I'm going to consider a loop which is made by 2 lines separated by an angle, pi minus phi, in our convention, on the big circle of S3. And these are extending along the time direction. It's very important for us. They are very long extending, so it's going from minus infinity to plus infinity, essentially. And I'm going to ask that the orientation of the 2 lines, there is a relative angle theta. This is what we call it the internal angle. So this is a bit the pictorial picture of the generalized cusp. There's been a huge amount of work, and I guess this audience is quite, you know better than me what has been done here. It's important to, at least for me, for this talk, what's important to remember that we can see the cusp in two different ways. So if I think of this picture, let's say once you weak rotate, you can interpret this potential, the Wilson loop, essentially as an effective potential between two heavy probe charges in n equal 4 super Young mills. So this is the one way to look at this Wilson loop, as an effective potential between a quark-antiquark pair. And of course, this is generalized what has been done in flat space, okay? And so, well, basically, this distance is giving you in flat space the distance between the quark-antiquark. And there are very important results, and they play a huge role, of course, in the history of the SCFT. But of course, we can use exponential map with rotate, and we can see this also as a cusp-Wilson line, that hence the name. And so now the angle between the two lines is given by pi minus phi, as we say before. And okay, we have to think about that there is an orientation between the two lines. This Wilson loop, having a cusp, has logarithmic divergences, and in particular, here I have, it's called indeed cusp anomalous dimension is what control these logarithmic divergences. And so since these are related to fast conformal transformation, we basically read, I'm going to switch, and sometimes I'm going to talk an effective potential between quark-antiquark, and sometimes I'm going to call it a cusp anomalous dimension. So here I'm underlined that there is lambda, of course, the two coupling that depend on phi, as I say, geometrical angle, and theta, the internal angle. Okay, I'm not done yet, in the sense that I want to do something more on this. What do I mean? I'm going to insert L local operators along the loop. Not any local operators, but I'm going to insert the scalars that are sitting here, Z and Z bar. And okay, in this picture, we are inserting to plus and minus infinity. And what is important for us, and these are the scalars which are not coupled in the Wilson loop. So these are sometimes called orthogonal. Okay, so in such a way there is no interaction. Okay, this plays a very important role, in particular, for example, for deriving the TBA of the cusp anomalous dimension itself. So this is it's an observable that plays an important role. I've added here an L because now this is going to be another parameter to add to the description. And okay, if I go back to the description of the cusp-Wilson loop, this for us is going to sit indeed at the cusp. So we are placing ZL operator at the cusp. Now, this is the object in the field theory side, but now I'm going to switch off to the dual side. So I want to study this object from the string theory perspective. And so we are studying this at strong coupling, so lambda is going to be large for us. But to have a semi-classical description on the string, we need to have also L to be large. So this is important because it plays an important role for us. Okay, so let me go to the string theory side. Well, I have to, maybe everybody knows, but a Wilson loop in the fundamental representation is holographically dual to an open string. And important to remember that the worksheet ends at the boundary of ADS5, ends at the loop itself. Now, the way that we can think about this insertion of operators, essentially in the semi-classical description, is like you are fluctuating your worksheet. And I'm going to be a bit more precise in a moment. And as I say, what's important for us to remember, there is a hierarchy of limits here. So there is a large N, large lambda, and there is also a large L, this R charge. Okay, so the plan now, since we are thinking about a semi-classical description, what we need to do is, of course, first look at the classical solution. So you have just a classical open string in a DS5 cross S5. And then we want to go beyond one loop. So this means take into account correction for strong lambda. And so this means, so basically look at the series 1 over square root of lambda. And so we are looking at fluctuation around this classical string solution. Okay, that's the plan. Okay, so for the time being, I'm gonna focus on the classical string solution. So just to which is dual to our observable. And this was obtained quite some time ago, actually. First in Drucker Kawamoto in 2006, and in particular for the case when you have the insertion on the straight line, okay? And then was generalized later with the two angle theta and phi. Okay, I'm gonna spend some time on that because it's important that it comes out, you understand what the object that we have. So, okay, the string worksheet coordinate, tau and sigma is between an interval minus s half, and we are gonna determine what it is s in a moment. And so what do we have? So let's look first on the IGS3 part, which is inside IGS5. So, okay, we wanted the worksheet end at the boundary on the loop. So this t of tau, it's representing indeed the running along the two lines, the time direction. Rho is the radial coordinate. So the string, of course, is ending rho going to infinity. It's the boundary of ADS. And then, of course, the string, it's moving inside the bulk. And then this is an angle, so there is a rotation. This is written here in this embedding coordinate. And this is the angle that when you reach the boundary is going to give you the geometrical angle of the quark-antiquark. So the separation of the quark-antiquark has to be pi minus phi. Okay, and then, of course, there is nothing else in the other two orthogonal direction. Now, if I look on the compact part on S5, what do we have? Well, okay, there is theta, var theta, I should say, which is, again, it's connected to the jump on the S5, that the cusp, remember, there is an orientation of different orientation between the line. So this is, of course, is related to that. But then we want to insert the operator. So there has to be an angular momentum. And so this is the omega tau that is going to describe the angular momentum related to the R charge. Now, notice that what I was trying to say before. This is in two planes which are orthogonal, okay? And so this is, of course, is the plane which corresponds to the coupling of the scalars. And then, of course, y5 and y6 do not play a role. So important for us, this is related to theta, the internal angle, and this is related to the R charge. Okay, this is a pictorial picture. Well, I don't know if hopefully it doesn't confuse more than what it's supposed to be, but it's just trying to put in picture what I'm trying to say. And of course, this is the boundary condition that I was trying to explain here. So when you reach the boundary, you need to reach the Wilson loop, which is described by the two angles, the geometrical and the internal angle, okay? Okay, let's see what we, okay, this I said in Word. So I'm not gonna go, well, okay, maybe one thing that I forgot to say, it's in this picture, the two insertions are basically at plus and minus infinity. I'm working in global ADS coordinates, okay? So what from the discussion before, the induced metric of the worksheet, it's ADS 3 times S3. It's written here. And let's start now to understand the parameters and the charges that we have here. Okay, so if we look at the equation of motion, d and omega, so these are depending on the tau coordinates, going from minus to plus infinity. So these are essentially given by they are proportional to tau, the worksheet time, and kappa and gamma. These are two parameters for the time being, okay? And we are gonna say more about that in a second. There are, of course, the correlative conserved charges, E and L. So in particular, E is the conserved charge with respect to time, and then L with respect to the angle omega. There are also two conserved momenta, since we have cyclic coordinates, and in particular, there is L theta for the rotation on theta, and, sorry, this should be actually var theta, sorry, and this L phi related to the angular momentum, it's the angular momentum related to the angle phi. Okay, so that's the setup. You can compute, for example, in conformal gauge, you can use Polyakov action to compute your string action. And of course, still I have to tell you the equation of motion for rho and for psi, the angle, in S5. And actually, it's easier to work with the Virasoro constraints. And these are the two Virasoro constraints that we have. Okay, they're important to notice that there is a kappa and L phi, and here there's a gamma and L theta. And of course, I mean, if you see it, there's basically an analytic continuation, one of the other. Okay, so there are two conserved charges, two boundary data, the two angles, and there are four parameters, okay? Gamma L theta and kappa L phi. But this is not the end of the story, because there is an extra relation. I told you about the extension of the string, which is S. And of course, you can compute this parameter either integrating rho or integrating psi. And so these two quantities, they have to be equal. This is nothing that say that basically you have to impose the Virasoro constraints. That's another way that you can think about this relation, okay? But it's going to play an important role. Okay, so these quantities were already computed in 2012, but I'm going to go over, because there is a technical caveat that's going to play a role for us. So please bear with me with the technicalities, and if it's not clear, just ask me. Okay, so we can switch. It's easier to work on with the Virasoro constraints, switching coordinates. So I'm going to switch to this R. GS stands for Gromov-Sever, since this is the notation used, for example, there in 2012. And I'm going to look at the Virasoro constraints. And okay, this is a quantity which is positive, so left and right side should be positive. So first of all, you analyze immediately that this gives you a fact that there is a minimal distance. What does it mean for the string? The string is moving when sigma is going to 0 to the center of ADS and reaches a minimal distance, okay? It's not necessarily, it's not reaching the center of ADS. Okay, but in order to integrate this equation, you have to tell me where is the order of the poles. And so if this A minus is less than -1, then you are scanning, let's say, the parameters L5, which are between -1 and 1. This is just, math. It's nothing more than that. And then for the second region, so if A minus is greater than -1, once you integrate, you are integrating in a region which L5 is between -1 and 1. So what does it mean, this one? This is simply you are living in this space of parameters, and the two regions are simply related by modular transformation, because once you integrate here, you're going to get an elliptic functions, elliptic A, elliptic kappa, and so on and so forth. And these two regions, so when you're switching from one to the other, are just simply related by modular transformation. So it's important to understand there is only one energy if you want. It's just that this is a way to, to avoid to deal with modular transformation. You can think also in this way. Okay, all this, so this A and this B is going to label to remember myself in particular in which part of the parameters I'm looking at. And these are all functional L phi and kappa. And this is what I was saying before. Okay, you can repeat the same story for the compact part. But slightly different, because now you have a sign of psi, which has to be always between 0 and 1. So in some sense, okay, you have still a minimal distance. This is telling you how much the string, once you move it towards the center of ADS, how much the string is reaching. So there is a, let's say, a minimal distance, also minimal radius on the sphere in which the string is sitting, and it's keep on rotating. And in particular, as I say, since this is a sign is always, it has to be between 0 and 1 if we want to have physical solution, this is imposed basically only one region. So you can scan between the parameters only between -1 and 1. These are the physical one. Okay, and so also L, theta, and S are all function of these parameters, gamma and L theta. In particular, L theta has to be between -1 and 1. Okay. Here, just to make you understand, because these letters maybe don't mean anything to you, but essentially when you are reaching 1 and -1, basically you are switching off. No, basically you are switching off the air charge, just to understand. And if L theta is equal to 0, this means essentially you are switching off the jump on the sphere. Okay, so basically you're switching off the angle, the internal angle theta. Okay, questions about that? Is it kind of clear what I'm saying? So here I'm just analyzing classical solution and dividing the different parameters, just for understanding. Okay, what are the consequences of this, if there are any consequence? Yes, this is what I was trying to stress before. Everything is continuous. There is only one energy, one cusp. Everything is continuous. Okay, so this is exactly what I said before, just rewritten here. There is another small caveat that I have to tell you, is where is among the So as I said before, we have this S, which is the interval in which the string coordinate it's spanning. And if I'm looking at the value that we can obtain from the parameters available on the compact space, this is spanning between 0 and infinity. But if I'm looking at the value that that I can compute, starting from ADS quantity, there is an interesting distinction. If I am in the region A, so this L phi greater than 1, oh wow, 10 minutes, okay? Okay, see, thank you. Then it's only between 0 and pi. And if I am instead in the second interval, so when L phi is between -1 and 1, this can span between 0 and infinity. So one case is bounding, the other case is not bounding, and this plays an important role. Okay, this is the string action, and I'm going to use G, which is basically square root of lambda, quite a lot. Okay, so somebody could say, and then what? Here comes the point. So I'm going to focus on the energy, and in particular, I'm going to look at the potential energy. So how do I think to this energy, the quantity that we are discussing before? Well, I'm looking the potential energy as the energy between these probe charges at strong coupling, and I want to study this in presence of this local insertion. And so I'm thinking about that as energy, let's say, as an excitation of the energy among the quark-antiquark. That's one way of thinking about it. And I'm going to take in doing this, what I have to look at, I want to look at these anti-parallel limits. So this means that we are taking. Okay. Well, then you have to sit down and compute. And what do I get? So if I am in region A, what do I get? Not surprising, something which goes like pi minus phi. This is indeed the quark-antiquark potential. This is the Coulomb-like singularity that we all expect and that we have been computing in the past. And then correction, which goes like pi minus phi and so on and so forth. So this coefficient, these are functions of the parameter K naught, and this is a combination of L phi and kappa. It's just as convenient for this relation, doesn't matter for us. But this has to be computing, and of course you have to impose the Virasoro constraints. So this means you have to satisfy this equality. What does it mean here? Just to be clear, I'm fixing L and theta, so this means I have an S compact, if you want, SS, and then I need to match, of course, the Virasoro constraint. So I'm going to find my K naught in such a way that this equation is satisfied. Otherwise, I have no string solution. Okay, I can repeat the same exercise for the B region. And what do I get? Well, I'm taking the limit, phi goes to pi. I'm going to take an L and theta fix, and I get something completely different. What do I mean? So it's a constant plus correction, which are actually quadratic in pi minus phi. And again, this is the parameter kappa naught, which has to come from satisfying the Virasoro constraint in this region. Now, there is a difference. This value is spanning between 0 and pi. Here I'm spanning between pi and infinity, okay? So this is something that needs to be understood correctly. So here I'm zooming to very close, so you see this is the behavior, and this is the typical Coulomb-like potential. Okay, so how can I understand better what's going on? So instead of fixing L and theta, what I'm going to try to do now is fixing theta and see how this energy changing when I vary L, okay? So it's just slightly a different approach. Now, where is the problem here? Let's say the problem. When I moving from one region to the other one, so basically the value of pi, you see, this is the value that, it's basically delimiting the two regions A, what I call the two regions A and B. So what I am going to do now, I'm going to focus essentially in the value of this S compact, which is fixed and close to pi. And for the way that we are constructing the equation, the solutions, essentially I can keep this fixed by either varying L or theta. What do I mean by that? There is an entire value. So you see this region, if I'm looking here, so here are all the points in which I have all this S fixed. So this is the interval for the strings fixed to pi. And these are, I can choose different, for example, I can fix L and vary theta in such to keep this S fixed to pi, or vice versa. So this S plays a kind of a role of an effective angle. I don't know if this is clear or I'm confusing you. It's kind of clear what I'm saying. The silence usually is not a good sign. It's like when you ask to the students, do you understand? Silent. What I'm trying to say is that essentially you have three quantities, S, L, and theta, but you have two parameters, okay? And so you can play with that essentially in such a way that, as I say, you fix the interval to be pi, but you can, how you reach this pi, you can choose either varying theta and fixing L or vice versa. And so this is the, this region. So I call it critical line because this is the pi, it's the value that separates the two regions A and B above pi. Okay, and so if I use this information and I'm look how the energy is varying with L minus L critical, so here I'm fixing theta now, varying L, and I'm looking the two regions how this is varying. And you see immediately, so we are still in the antiparallel lines, we are only working the antiparallel lines. There is this 3/2 coming here, and there is 1/2 coming here. Okay, 5 minutes. So what is going on here? So here the energy is negative as we expect, and this approaching the critical value with an exponent which is 3/2. When you reach the L critical, the energy vanishes and it's start to increase. So this is actually positive when you move to the next region. So, and in particular, it's increasing with a power which is 1/2. So the energy quantity is continuous, but of course it's not differentiable. You can compute this quantity here, it's just an expansion, Taylor expansion. So we have it also, of course, either numerically or analytically. So this is a plot in 3 dimensions. I can see now it's very pale. This is the plane, which is L equal to L critical here, and this is the energy versus L, and these are the value of phi. So towards here you have pi, and this is going to 0. Okay, so this is what it's going on. So as I say, it's continuous but not differentiable. Okay, so the question is what is going on? I think the main message was already understood quite some time ago. So the classical solution here, what it's doing, encodes this transition from the Cass-Wilson loop, basically when you have L equals 0, you don't see the insertion, to a kind of BMN-like vacuum, where you see only the insertion. This is what's kind of, I think it's the correct message here. What does it mean? Well, it's basically you are, I think also maybe it's clear in the spin chain picture, you have this zeta L. When L is very large, you're basically probing this trace to the zeta L if you want. It's some kind of BMN-like vacuum. But if L is not that large, then you start to see the endpoints of the chains, which are basically this Cass-Wilson loop, which are, so it depends on the theta and the phi. So I think this is the message that we are seeing. And so they were looking, for example, for the special case of phi equals 0, this so-called Lusher correction or wrapping correction along in the paper by Correa, Maldacena, and Sever in 2012. So when L starts to be large, so your L, as I say, you are proving basically the size of the chain, the energy minus the L, it's going to 0, so it's kind of going to a BPS state, but with the exponential correction. And we see this in our computation with for generic phi and theta. Why this is important for us is essentially we need this region to reach this value, because here we are always bounded to have a maximal L in some sense. So if we want to approach very large L, we need to be in what we call this region B. So this is the one that allows you to connect essentially with the BMN vacuum and with the Lusher correction from the spin chain point of view. Okay, so this is what I'm saying in Word. Now, I can look also, so we talk about BMN, and so we can think about also, can we see this BMN spectrum? So this is an initial analysis was done in 2006 in the paper, as I said, by Drucker and Kawamoto, and we see this coming out from one-loop computations. So if we have the full Lagrangian for the one-loop computation, and we see the emergence of this PM spectrum. So if we take this large M limit, so and again, this has to be connected again to the large L. So it has to be coming from region B. So okay. Okay, there is another paper which is playing an important role. Okay, then I'm just suggesting one sentence of this paper. So this is a paper from 2006, not very cited. And they were studying the quark-antiquark potential in flat space-time in the presence of these L massless scalars field. And there, the way that they think about, okay, it's in the language of QCD, this quarkonium, they interpret this going to zero of the energy like basically the binding energy, it's vanishing. So after that, you have an unbound state. You are describing unbound state. But for some reason, they did not continue. So they kind of stop at zero, and they do not move for, they don't have a region B in some sense. That's the way of thinking in our language. Okay, what about loop correction? Well, the question that, as I say, I was trying to answer before, do we see the BMS spectrum? Well, the quick answer, since I have less than 1 minute, yes, at least from the analysis of the frequencies that we have been doing now. And the other question that, of course, is crucial for us, does this transition, I should call it quotation mark transition, survive at one loop? As far as we can see from the analysis of the frequency that we have, the answer is yes, even in some sense it's a kind of a classical mechanism. And bosonic for the fluctuation, so these are fluctuations around the classical solutions, and we are studying the frequencies for these modes, and so far what we have been doing is just looking at the so-called easy modes in some sense, the one which are decouples, because it's a bit, well, the masses are not that trivial to, in order to compute the frequencies. Okay. Okay, that's what I was saying more. That's the summary. And I guess I have 0 minutes. And that's the to-do list. So I'm going to just focus on the to-do list. Of course, we want to compute the one-loop analysis, continue with the coupled, let's say, modes. We want to look also for different limits. So here we focus on the anti-parallel limits, but we want to look, for example, near BPS limit. If there is something we can say, this is all strong coupling, at the correction strong coupling, so we would like to see if there is something that can be said from, there are data coming from the quantum spectral curve, from the TBA, so can we say something about that? And then there are, of course, many other things to be done, so this is just a list of the one that I think I consider interesting to explore. Okay, thanks for your attention.
Okay, so questions?
Hi. So could you remind that at weak coupling, I think there is pole at any L if L is fixed at weak.
Say it again, sorry.
At weak coupling, there is a quark-antiquark pole at
yes,
any L.
Yes, that's true. That's true. That's true. That is also true at weak coupling. Yes. Is that?
So near L critical, if you consider L to be continuous, what kind of, how did you analyze the transition?
Yes, that's classical level, you mean?
Yeah.
Yeah, this is what we are looking here, essentially. Well, both for the action, this is always in the anti-parallel limits. So this means close to L critical, phi goes to pi, and then I take my theta fixed. That's the, and so this is, it's continuous, but there is like a kink in the action, and the same is true for the energy. I don't know if it's visible in this mathematical plot, but so the energy goes like that.
One last more question.
Okay, I feel a bit uncomfortable to call it transition because there is one solution. If I think of phase transition, I usually think about an interplay of different solutions, and then your free energy is as a king. I don't know, maybe, yeah. So there is one solution of the string, as far as I understand. So that's why I'm using quotation marks. And it's in some sense, yeah, that's the answer.
More questions? Well, if there are no questions, we thank Valentina again. So the next talk is by Stefan from Imperial College